Exercise 41. So let's follow that exercise 40, talking about least square problem. So there is a phenomenon of this least square problem, which is sometimes it has a unique solution, sometimes not. Okay. Let me just firstly give you the example. So first part, find all least square solutions to Ax equals b with this matrix A for right free matrix. Notice that the columns are not linearly independent. So let me just quickly give a solution of this part. So normal matrix is like normal equation is this one, right? To solve the least square solution is the equivalent to solve this x hat for this one. And then you compute this, you will say that this is equivalent to solve x hat here is just solving a 3x1 matrix. And then you solve it, you find that there are infinite many solutions. So the second part of the exercise is to give you criterion. When does it have unique solution? When does it have infinite many solution? It's very similar as the case of Ax equals b. In that case, we know that it is unique when it has solutions. It is a unique solution if this A has linearly independent columns, because, as I said, so this basically when x runs over all the possible vectors, Ax runs over the column space of A. It is a linear combination of its column vectors, and vector b, if it's in this plane, then it is a linear combination, and this linear combination is unique if all the column vectors of A are linearly independent. If they are not linearly independent, then there will be infinite many solutions, right? And the question is now, for the least square problem, when will this be has least square solution? When will this least square solution be unique? In this case, it will always have a solution, because least square problem always have a solution, because we're only solving X equals this b hat. This X equals b hat always have a solution, because b hat is by definition the projection of b into this column space of A, so it is in the column space of A, and so in particular it have a solution. It is a linear combination of column vectors of A. And when does it has unique solution? Similarly, it's the same answer. When these columns of A are linearly independent, this has a unique solution. Okay, so let's prove this. As first state, what do we want to say? The following are equivalent. Ax equals b has a unique solution. I mean a unique least square solution. X hat for all vector b in R. Here I'm talking about this a n by n. This is n by 1. This is n by 1. Again, we're talking about R into Rn, matrix multiplication, sending x to Ax. We want to characterize this unique solution by columns of A linear independent. Moreover, and one more characterization, ATA is invertible. Okay, so let's give the solution of this. Let's first show that 1 implies 2, A implies B. Suppose it has a unique least square solution for all B, in particular for B equals 0. Has a unique solution, has a unique least square solution. But least square solution, how do we characterize it? This is equivalent to say A T A x hat equals A T 0 has a unique solution, right? But notice that x hat equals 0 is a solution. This is telling that x hat is the unique 0 is a unique solution for this. So this is equivalent to say A T A x equals 0 has unique solution is hat equals 0. This is equivalent to say what? A x hat equals 0 has a unique solution because if not, then ATA x hat 1 is another solution. Let's see, you have two solutions. First is x hat 1, second is x hat 2, and so both equal 0, and this will both become a solution of this ATA x equals 0. Contradicting to the fact that ATA x hat equals 0 has a unique solution. Has a unique solution. Okay. But when this has a unique solution, this is equivalent to null space of A equals 0, and hence columns of A linearly independent. So this A implies B. Let's say B implies C. So I want to show that if the columns of A are linearly independent, then A transpose multiplication with A is invertible. Again, so B is saying that columns of A are linearly independent. Columns of A linearly independent would imply AX equals 0 has a unique solution, which is 0. Notice that ATA is square. So A is n by n, this is n by n, this is n by n square matrix. So it is invertible if and only if it is 1-to-1 as a matrix transformation, if and only if it is onto as a matrix transformation. So 1-to-1 would correspond to, that's invert it as linearly independent columns. It's also equivalent to say has a unique solution. But what does it mean? Suppose this is 0, we want to solve it. Let's see. If we could prove it has a unique solution, then we prove it is invertible. But this is equivalent to it's not equivalent, but it implies this is 0. This implies this is 0. This implies this is 0. This implies the length of X is 0, implies X is a 0 vector. And B implies that X equals 0. And so it has unique solution. And so it is invertible. Finally, C implies A. Suppose this is invertible. And we consider starting question X equals B. The least square solution is a solution to our normal equation ATAX hat equals ATB, right? If this is invertible, then we have a unique solution, which is right, and so this is finished. So let me put third part of the exercise. The last question is, suppose A is n by n matrix with linearly independent columns. And so in particular, by the second part of the exercise, it has a unique least square solution. Write down the unique solution by Q and R, where A is linearly independent, so by QR factorization, A equals some QR. Okay. Solution. So X hat would be R inverse QT and then B, because you just put it into your solution, you will see that it satisfies that. Linear square, least square problem. So we claim this is the unique solution for A X hat equals B hat. This is the equivalent description of the least square problem, but because this is kind of difficult to solve, we introduce that normal equation, right? But let's check this works. So A X hat equals A R inverse QTB. This is A equals QR R inverse QTB. This is Q and QTB, but Q and QTB, if you remember, so Q gives the identity, but QTB actually gives you what? Gives you projection of B onto the W. What is W? W is the span of the column vectors of Q, which will be also the column vectors of A. And so, which is exactly our B hat. Okay, so this is obvious. This is by previous exercise, if you want, exercise 39. So to say this is the projection of D, this is also very quickly. So just recall that your A is A1, A2, AN, and then you got your after Gram-Schmidt process plus normalization. We got U1, U2, UN, and we call this Q, and so Q, Q, T, B would be just by definition U1, UN, transpose, U2 transpose, UN transpose, and then B. So think of this as n by 1 column matrix. Think of this as so U1, each U1 is n by 1, and so it's transpose 1 by n. So altogether it's n by n. Sorry, of course this is n by m because this is a 1 by m, so you have m columns. Okay, but you think of this as one by one column vector. Think of this as n by 1 column vector, and then this multiplication could also be written as basically what we're doing is we use block matrix, right? The same rule for multiplication also works for whatever kind of blocks you want to use. And so this is also U1 UN multiplication. This is a dot product. And so finally this is just summation of B dot product with UI, and then times I from 1 to D. This is exactly our definition of projection. This is a formula. We project B under orthonormal basis, and that would be a linear combination of these orthonormal vectors. What is the coefficient? The coefficient in general it's given by, if you use projection y onto some u, the projection would be y dot product with u dot product with u, and then collinear with u. This is general formula, but because we are orthonormal, we don't have denominator. The denominator equals 1. And so this equals that one. Okay. Basically, you could think of this as some exercise showing that this projection will be onto a column space of A could be computed using QQTB. So think of this as some exercise, that solution of this is here. So we have finished the proof.